All right, Math 125. We're looking at law of sines, law of cosines this week, and I didn't really put much in Monday, hardly anything about law of cosines. I want to introduce that now. So I am watching for questions on here if they come in, but I'm going to introduce the law of cosines and when we need to use it. It's complicated, more so than law of sines, and so there's a lot of calculations involved, but we need to we need it in a couple of situations with triangles just to get started on the problem, because we don't have enough information to start the law of sines and solve for anything. So if you're thinking you want some more practice with law of sines still, well, it's kind of built in here because we're still going to be using that to finish these problems off. We'll be using law of sines in the process here, so you'll see how that works also. But we've got a few here that, because of what we know and don't know about the triangle, we got to start off with something different, and I'll explain kind of how it works. So I'm going to get this situated and chime in as we go along. So this is one I copied out of the section in the textbook that covers law of cosine. I don't remember the section number, but number 24 here was a triangle that we're trying to solve, just like we did before. But you can see the given information here. I just copied the drawing down so we'd have it on paper here where I can work on it. So we know an angle here is 48 degrees. I'm going to try to write larger. I'm trying to get in the habit of writing bigger because this camera isn't the greatest. I got 48 degrees right there. And the side lengths here, I don't know the units, but this is 14 and this is 22 were the side lengths. So we're trying to find the third side length on that one. Not sure what's happening to the video at this point. But we're trying to find the other side, and along with it, these two angles right here to solve the triangle. This looks like a 90-degree angle, but I don't know if it is. I don't think it's going to be exactly 90 degrees. So don't know if it's exactly 90 degrees. We're going to have to give that a try and see what happens. The law of cosines applies anyway. But if you're looking at this and thinking 22 squared and 14 squared and this squared, if you're thinking about Pythagorean theorem, you're not too far off. On a right triangle, before we get to this problem, let me explain what we got here. On a right triangle, a squared plus b squared equals c squared. Or I could write it this way around. If we're finding one of the sides, we can use this relationship. That's only true when the angle C is 90 degrees. This is perfect, comes out perfect to c squared, and you can solve for a third side there without having to think about the angles. That's nice. If angle C is a little bigger than 90 degrees, if this was actually a little bigger than 90 degrees, then you can see side C is going to get longer. And if C was less than 90 degrees, side C is going to get shorter. So if we're solving for that C, if we're not talking about a 90-degree angle there, there's another piece to this out here that gets bigger when C is greater than 90. And I'm not going to really derive where this comes from, but I'm going to write it down and kind of explain how it works. This is 2 times A times B times the cosine of angle C. So that's capital C that we're using for the angle. So that's the cosine of capital C that we can find. Now, if we know A and B and this angle, we can solve all of this out. We can find little c, just taking the square root of all of this, and we'll have it. If C is 90 degrees, cosine of 90 degrees is 0, and we just get the Pythagorean theorem. So that would be okay for that one, for the 90-degree situation. If C is bigger than 90 degrees, the cosine is going to come out negative. So this is a minus here, we'd be subtracting a negative, and we get a bigger value for little c, which makes sense here. If the angle gets bigger, little c is going to get bigger along with it. So this extra term we got to put on here, and I like to kind of group things together. I might not put parentheses, but we want to think about those groupings. This cosine is just multiplied by this one term, so we want to put this together first. This is what we're going to apply. Now, since we're applying this to triangles that don't have a right angle anymore, there isn't any magic designation to the letters. It doesn't matter which one we call A or B or C. So let me write the others down while I'm making a point on that. If this is true, we could change the labeling around. If we were talking about A squared on this side, then these two would be B squared and C squared, and this would be 2BC times the cosine of A. That's going to change to angle A in that one because it's the angle that's across from the side that we're putting on this side of the equation. That's how this works. Whatever letter is over here, the side that's over here, the corresponding angle is going to show up here. The other two sides are added together here and multiplied here, and it's the cosine of this angle. So all three of these are true. We're not going to need all three of those on any given problem. We're going to use just one, and we have to think about which one will apply to our situation in the problem we got. It's really just a matter of different labeling. All of those are true, and we can use this if we need to solve for an angle also. There's only one angle that shows up in here, but if we know all of the other letters, the side lengths, we could actually solve this for cosine of A and solve for angle A that way. We'll use it that way sometimes. All right, so that's the extra term. It's kind of there. Pythagorean theorem is a special case here for the 90-degree angle, but this is what's really true about any triangle. And we're going to put that to use on this one here. So here they don't come labeled, they came drawn in the picture instead, but I'm going to attach a labeling so we can use the formula and have the letters to keep track of. And it really doesn't matter which is which here. So if I call this one A, and this one B, what does matter is the arrangement right here. If I decide to call this side little b, then the angle across from it is capital B. That's one of my unknowns. And I called that one A, so the angle across from that is angle A down here. And the 48 degrees would have to be angle C then. And this side would have to be side C. So they're across from each other. The angles are across from the sides. That's the law of sines works nicely on this. But notice what we know and don't know about this one. If I tried to set up my law of sines, let me organize it over here, what we know and don't know, and make a point. I like to make the little chart this way so everything kind of stays together. Angle A is unknown. Side B is 14. Angle B is unknown. Side C is unknown. Angle C is 48. If I tried to set up my 48 degrees, if I tried to set up my law of sines with A's and B's, I got two unknowns in there. And if I tried to do the law of sines with B's and C's, I still got two unknowns in there. Any little combination, I have too many unknowns to actually solve by law of sines. So this is one situation where the law of sines doesn't help me get started on the problem. If I can, I'm going to fill in one more blank, and then once I have one more blank full, I'll have enough information to solve it out from there using law of sines. But it doesn't give me enough to get started. That's when we need the law of cosines. This situation, we know two sides and the angle between them. So I'm going to try to solve for little c. It's really hard to break the habit of using a squared plus b squared equals c squared when you see them written like that if you're used to working with right triangles. But we have to get away from that now because that doesn't apply here. Well, if cosines applies, which is similar, but I'm going to solve for little c using this thing. So I'll write it down again. And then I'm going to use, well, I'm going to drop in the numbers that I know in this thing and see what we got. So C is the thing I'm solving for. A is 22. I got 22 squared plus 14 squared minus 2 times 22 times 14 times the cosine of 48 degrees. Here's where you got to watch your order of operations. You got this great big expression right there. But we're going to do this calculation. We're going to do this calculation. We're going to subtract at the end. That keeps all the order of operations stuff straight. So that's why I'm going to work that out. Now, I don't have calculator I can put on screen for this. I'm going to do the calculations off screen and put the results down. If you're following along with this, you can punch the numbers in, make sure you're getting the right thing. We do have to be careful about the way that they're grouped, and kind of the order of operations is key to this. So be careful with it. Be careful with the parentheses in the calculator and all. This is real. Notice what we're getting is C squared. I'm going to have to take a square root later. We'll get to that. So I'm doing the 22 squared and 14 squared. Comes out 680. And I'm going to do this calculation. 2 times 22 times 14 times the cosine of 48 degrees. You want to make sure, if you're doing this in a calculator, and you should be, you want to make sure that you're in degree mode for this. We did the graphs, we used radians, but for triangles, we use almost all, this should all be in degrees. So you want to make sure you set it back to degree mode for the law of sines, law of cosine stuff. That could throw you off. Cosine of 48 is where that's going to make a difference. That part comes out 412.2 approximately. I'm rounding that. This is going to come out positive, as it should here. C squared equals, I will do the subtraction there. I get 267.8. So C has to be square root of that. Equation-wise, if you're a big-time equation person, you're thinking, wait a minute, we're taking a square root of both sides. We should say plus or minus right here. And it'd be good if you caught that. But in this case, we're talking about a side length in a triangle. We're not talking about negative values right here. It's not really applicable. So this is 16.4, approximately 16.4. That's rounded, but that's the value for the third side in this. 16.4. I'm going to put that in here in my chart. I don't really do much, honestly, with the drawing on these things, because I don't even try to draw them to scale, really. It's this chart that really helps me organize what I know and don't know. So when I'm doing triangle problems, right triangles, law of sines problems, law of cosines problems, I just like to keep this chart organized with what I was given and solve for the other stuff as I go along, so I can keep track of what I need. $16.4 I ended up with there. So that's the in-between side on this. Okay. Now I have enough to get started with the law of sines. I could use the C's and the B's in the law of sines, or I could use the C's and the A's in the law of sines. It doesn't seem like it ought to matter, but there's a little strategy to this when we get to this step. We're going to have to solve for both of them, but I'm going to give you a little strategy on this. I have a situation where there's two unknown angles left. Strategy says to solve for the smaller by law of sines. And the reason we have to be strategic about this is because the law of sines doesn't know the difference between the first and second quadrant. Angles bigger than 90 and angles less than 90. The sign comes out the same on either side, and you can't tell the difference that way. So I want to use this for the smaller angle, and then we'll find the other one from, well, just from the angle sum property, so we'll know for sure. So that's why the smaller one works. Now, if you're thinking, how do I know which one's smaller when I don't know what the values are? That's a good question. So I ask myself a good question here. But to answer it, just geometric reasoning on this. It's a fact about triangles that the biggest side is across from the biggest angle, and your smallest side, these were close together, but this ended up being the smallest side. That's going to be the smallest angle. That's the way it works. Your biggest angle, biggest side, smallest angle, smallest side. So by looking up here, I can tell that angle B has to be the smallest angle involved. That's the one I'm going to go for law of sines. So that tells me that sine of B over B is equal to sine of C over C. Notice when I put that down, I can solve for one unknown in it. I have three numbers and one unknown. That's what you want with law of sines. We can cross multiply and solve it out for sine B, and then we can get angle B from that. So if you haven't worked through law of sines problems, this is what they look like. You know two of these things and one of the other, you can get the fourth one from this nice little proportion problem, so it keeps the algebra a little simple. Write it down, cross multiply here. 16.4 sine B equals 14 times the sine of 48. Then I have to divide by the 16.4. I'm trying to get the capital B by itself. So this is the calculation I want to do. I'm going to go off to the side and write down what sine B comes out to. And then I have to think a little bit, but I'm just doing the algebra to solve for sine of B first. So calculating that out, and I'm doing 14 times sine 48 degrees. Get that answer and divide it by 16.4. So you got to be careful with your order of things here, but that whole thing divided by 16.4 should come out 0.634. I'm rounding here, but I'm not, well, keeping a few decimal places, and I'll round off the result on this. Here's where you have to use one of these inverse trig things, because the sine of B is 0.634. What angle has that sine? That's an inverse sine situation. So here's where I'm using that second sine or sine inverse, whatever your calculator setup for it is. You have to use that inverse trig. Your input is that number, and that's going to give you an angle. And if you're in degree mode, that'll come right out as a degree measure right there. Let me do those calculations off to the side also. That should come up to 39.3 degrees. So if you're getting different things in the calculations, that happens a lot because we got some heavy calculations going on. Let me know where you're getting stuck if you can't find your way out of it. Make sure the mode is right, that you're in degree mode. This should come out. So I'm trying to write down this step so you can follow that and make sure you're getting the right thing as you go along. It's a lot of work right here, right? We're still on the first problem. I spent a lot of time on this. I'm explaining it as I go along, but it is time-consuming process to really go all the way through on one of these. There's a lot of work to it. But 39.3 is my third angle. We're almost done now. Capital B is 39.3. Sure enough, that's the smaller angle here. Approximately 39.3. That's rounded. And then I get my third angle, since the three angles have to add up to 180 in a triangle. I just want 180 minus both of these things. So I'm just going to take away the ones that I know from that 180 degrees. They're all degrees. I don't really need to mark to do the calculation. But I'm going to do that subtraction now and see what I got left. Leaves 92.7. So when you do that subtraction, you get 92.7 degrees. That is the measure of angle A. It ended up being close to 90, like the picture. We kind of thought that from looking at the picture. It is. It's close to 90. It's a little bit more than 90. And that's the big warning that ties to this strategy right here. If I used the law of sines to find A, it wouldn't come out in the second quadrant because this inverse sine never comes out as a second quadrant angle. It doesn't know that you're in the second quadrant. So it wouldn't come out right for a problem like this. That's why we go for the smaller of the angles first. And this smaller one is always a first quadrant angle. And so the law of sines won't throw us off if we're following that strategy. That's why I was able to take this inverse sine down here and not have to worry about what quadrant it comes out in, because I know I'm going for a smaller angle here. The other one wouldn't make sense in that case. So that's the smart strategy I know. Good news about this, in the law of cosines problems, there's only one triangle. There's never two different answers that work. So if you've been doing some law of sines problems and you ran into this case where there's actually two triangles, actually two sets of answers, that happens with the law of sines, but it doesn't happen with the law of cosines situation. It shouldn't happen to you here. There is a little strategy to it. Notice what we knew to start with on this was two sides that are next to each other and the angle between them. So if this has to be 48 and this has to be 14 and 22, nothing can really move in all of that. So there's only one way to put those together at a 48-degree angle. So there's only one triangle that fits it. There's not going to be more than one possible triangle from that. You can run into ones that don't make sense at all. I mean, I could make up numbers that don't fit together at all, but you're not going to run into any with more than one solution here because of what we're starting with. All right, I'm going to grab another one out of the book to start with. There's one other situation where we need the law of cosines. This one was given two sides and the angle between them. We had to get started with law of cosines. There's one other situation that I want to make sure I do one of, so I'm going to grab one of those out of the book. But there's the case where we know all three sides to the thing. What if I'm given this information about it? A, B, and C are all known, and none of the angles are known. Then I don't have enough to start with law of sines there either. So I'm sure there's some of those in the book. I'm going to grab one of those. Number 16 in the book is one that has this situation. A is 10.6. I didn't put any linked units on it, so whatever the units are, doesn't really change anything. B is 8.5. C is 11.3. So if you had three sticks that were those lengths, you could form a triangle with them, and there's really only one way to stick them together. I mean, it could be upside down or rotated, but it's the same triangle if it has those three side lengths on it. We should be able to find what those angles are, but you can't get started with the law of sines to do that because you just don't have enough information. If you try to set up your proportion with A's and B's, you just got too many unknowns there. It's a little dark, but I'm going to try to do. Well, I'm going to need the law of cosines on it. But I don't know which version to use. Here's where we need the strategy again. Here's where you got to make a choice. There's not a lot of places in math problems where you get to pick from your different options. And I know most of the time math students are a little scared if they have to pick from different options. But this strategy narrows it down from us. We're in a situation right here where there's three unknown angles. Right, my law of cosines is really three different laws. I know all three of these things. And if I know all three sides, I could really get started with any of these and solve for the unknown angle over here. I could actually do any of them, but I could do them all, but this is such heavy duty calculation that I want to do this the easiest way possible. And I don't want to have to worry about quadrant things. So I'm going to solve the largest angle first. This is kind of the other way around, but I'm going to solve for the largest angle. Using law of cosines. That's the nice thing about cosine. If you haven't yet picked out a favorite trig function, here's an argument for cosine, is that cosine knows when you're in the second quadrant. Right? Cosine's positive in the first quadrant and it's negative in the second quadrant. So if there is an angle bigger than 90 there, that's the way it's going to come out when we solve for it. Now, I want to know that. So I'm going to find the largest angle, and if it ends up less than 90, then everything's less than 90, and I don't have any of that to worry about. If it comes out greater than 90, then that's the only one greater than 90, and I still don't have anything to worry about. So I'm giving you some strategy to avoid some pitfalls here. Which one of these is going to be the largest angle? Well, it's the one across from the largest side here, so it's got to be C. In this case, the largest angle is capital C. So I'm going to write down the version of the law of cosines that involves angle C, and then I'm going to plug the numbers in and see what we got. So that's the one that looks like this. I think it's the same one we used before. But the one that involves angle C is the one that has little c by itself. But notice the way we're using it now, we're going to have to solve for this. So I'm going to plug the numbers in, but then I got a little bit more equation stuff I have to go through to get this by itself. And we're going to end up solving for capital C. Plug the numbers in. Trying to write large. C is 11.3. A is 10.6. B is 8.5. I started writing big and I'm running out of space over here, but this is cosine of C is part of this term. So I'm going to have to get the separate terms here and move some things around in the equation. But you do this calculation and this calculation first. You can do the multiplying here, but that stays on your variable term. Be careful about this. For some reason, people tend to put all that calculation together, but the only part of this is on the cosine C term. So you have to keep these two terms separate. The way that I wrote it didn't help there because I ran out of space, but I'm going to do this in this calculation. So 11.3 squared is 127.69. Trying not to do too many calculations at a time. Keep to a few operations at a time in a calculator so you don't get messed up with your parentheses and whatnot. But 10.6 squared plus 8.5 squared, I'm going to put that together. Those two terms, that comes out 184.61. And then I have the subtraction here. I'm going to do this multiplying. 2 times 10.6 times 8.5. It's 180.2. See, then it's really tempting. You have number minus number right here. It's really tempting to do that subtraction, but you can't because this is a cosine C term. We have unlike terms. And the number terms have to be done on the other side. So we're going to solve for this. We're going to get that term by itself and solve for cosine C. So the next thing to do is subtracting 184.61 from both sides. That'll get this term by itself. I will work my way down to angle C. One problem. Getting negative when I subtract right there, that's okay. 127.69 minus 180.2 is going to come out negative. That's okay. I'm I'm going to be doing negative divided by negative to get cosine C. So the next step is division. We're getting a little review of equation solving here, which is good because that's the big focus of the course that we got to get back to. What we do in the following chapter after this trig stuff is done is all different kind of equation solving. So we're going to get a bunch more practice with that. That's a good thing. This is how we get cosine C by itself. And then we're going to have to do some trig stuff. This division should be a small number. 52.51. I'm sorry. I just looked at calculations, realized I subtracted the wrong thing. This isn't the right number there. Let me make that correction before I go further. I punched the wrong thing in the calculator when I subtracted. 184.61 is what I'm subtracting. That's what I wrote down. This should be 56.92. It is negative, but it's 56.92. Now I'm taking that answer divided by 180.2. It's negative divided by negative, so it comes out positive 0.3159. Again, if you're watching this later, you got a chance to pause that, do the calculations, make sure that you're getting the same numbers. Make sure you're doing the steps in the calculator. But now we get to an inverse trig situation again. Getting C by itself means I need to get rid of cosine, but it's not a multiplied thing, it's a function thing. So I got to do your inverse function. I got to do inverse function, cosine inverse of 0.3159. Since that did come out positive, this is going to be a first quadrant answer. And that's okay. That'll take care of all of this. If you ended up with a negative here, which could happen, then inverse cosine is going to know it's a second quadrant angle. Either way, you can trust what you actually get from the calculator on problems like this. And it'll end up in the right quadrant. That's why we're trying to take care of that now, because inverse sine's not as good at handling them. But 0.3159, you get pretty big angle, but it's first quadrant angle. Should come out 71.6 degrees. You think all of that work that we went through just to get one of the answers to this problem, but it is quicker after this, right? The hardest thing is to get started on it. It's a little bit like filling in Sudokus, I guess. The first numbers can be harder, but once you get rolling, it's a little simpler to see. You know more now. 71.6 is angle. See, that's the biggest angle in this, so they're all going to be first quadrant. But we have something to fill in here, and so now I can set up law of sines to solve for the other ones. Two unknown angles, I'm going to get the smaller one first. So I'm going to work the law of sines for this piece. A lot of steps, takes up a lot of paper to write things down, but they're complicated enough that if you try to enter too much into the calculator, it just gets tangled up. So you're doing a calculation somehow, but you need to be writing down some in between steps as you solve these things out. For this, law of sines looks like B over sine B equals C over sine C. So when I cross multiply, 8.5 times this sine of 71.6 is equal to 11. Trying to get sine B by itself, so I'm going to divide. I'll do all these calculations and see what that comes out to. Sine of B should equal the result of all of this. Let's see what I get. Again, I'm going back to have a nice way to put it on screen, but I wrote it down thoroughly. 8.5 sine of 71. That result divided by 11.3. comes up to 0.7137. And now I need to do my inverse sine, knowing that this is 713. That should be 45.5 degrees. So that's angle B is 45.5 degrees. Now we're rolling on this thing. The last angle I always get from my angle sum property. So that's good. I can come back up here and fill this in. 45.5 degrees. And then 180 minus both of those. Be my third angle. That will finish off the triangle there. So once you know two angles, you get the third pretty much for free, just doing a subtraction problem. 62.9. That ends up being the in-between angle. That's the smallest side in the smallest angle. This is the biggest side in the biggest angle. A is in between. So that all looks like it should. That's a good thing to keep an eye on. Everything should come out fit in that pattern. Camera wants to go kind of blurry at places here, but A is 62.9. That's the full solution to that. We've solved all the parts of the triangle on that. So they are time consuming. I mean, it's a lot of steps to that. It's a lot of calculation and a lot to keep track of on paper. But that's if you have to solve for all the parts of the triangle. When it says solve the triangle, you got a lot of steps to do to get through it all. You got to use those strategies. Some of the problems are just going to ask for a particular side on it or a particular angle. If you only need to know one piece, you might not have to go through and get all of the other pieces. That would be okay, depending on what they're asking for in the problem. But a lot of these, it says solve the triangle, and that means fill in all the blanks in that chart. This one I did without ever trying to draw it. There's nothing I really get from the picture. It's the labeling, and that chart helps me organize the stuff, but having it properly labeled and working with the chart, I don't really need the drawing. It's not really that helpful, I found, in these problems. There's a lot that can go wrong in the calculations, but a lot of cosines problems, they do come out nice. I mean, they don't come out in nice numbers, but they do come out without any multiple solutions or anything strange like that. Let me do one of these others that's drawn in the book, but I'm going to write it down in chart form. So you got to do some kind of labeling on this. I'm going to do number 29 from this section also. I think I got time to work through one more. This starts with nice numbers. Probably don't end up with nice numbers, but number 9. Number 29. Right? Starts with the drawing, and I got a really long side. Well, it's 6 units, and this is 3 and 4. So I got a fairly long triangle, looks like that. Fairly long and thin compared to the others. If it's drawn to scale, which it's not now. I mean, I just do that down. It's not terribly accurate, probably, but that's the drawing. I need to label them somewhat, and I'm not going to work off from the drawing. I'm going to try to work off the sketch. So I'm hoping this is going to come into focus a little bit more at some point. I don't know. But I'm given all 3 sides. That's a law of cosines situation. A and B and C, whichever one I want to call, which it doesn't matter which I call them. So I'm going to go 6, 4, 3. Those are the 3 sides. The angles are across from them, but the chart keeps track of that. So I'm just going to go right to the chart form of that. A is 6, B is 4, C is 3. Angles are all unknown. I just got to fill in one of them, and then I can use law of sines and my angle sum property to fill in the other blanks on that. Typical. But got to get started, and I don't know enough to get started with law of sines because I don't know any of the angles. So here we go with picking out a version of the law of cosines that'll fit this. Following my strategy, I want to do the largest side first. I got 3 unknown angles. I want to find the largest angle first using law of cosine. So I'm going after capital A, angle across from the largest side. So I'm going to use the version of the law of cosines that has capital A in it, which is the one that has little a on the other side by itself. So this is a squared. I'm going to write this down again. I don't really need to, but helps to have the formula that I'm using written down and then drop the numbers into the containers that I have here. So B is 4, C is 3, 4 squared plus 3 squared minus 2 times 4 times 3 cosine of A. Easier calculation because it's starting off with nice numbers for a little while here. Wow, the not having a good focus day as far as the camera goes. I'm sorry about that. I'll try to get closer to the camera and see if it happens to help. Trying to compensate as best I can. But I got 6 squared equals 4 squared plus 3 squared minus 2 times 4 times 3 cosine A. That's 36. I'm putting those together. That's 16 and 9 is 25. I'm putting these together, and that's 24 cosine A. Really tempting to combine those, but I can't subtract. This is a term that I got to get by itself. So what I really have to do now is get rid of the 25, remove it. Subtract that from the other side. That came out positive over here, and this is negative 24 cosine A. So this is where the results look a little different. Cosine A comes out negative. You should stop and think when you get a negative result, if you're doing geometric stuff, you know, what's allowed to be negative? That's a little weird. But this is okay here. This is 11 divided by negative 24. I'm going to go ahead and write that as a decimal. Negative 0.4583. But that's not one of the angles or the sides. That's the cosine of A. Cosine of something can be negative. That just means you're in one of the quadrants where cosine is negative. Now it has to be second quadrant here. You can't be over 180 degrees in a triangle. So this has got to be a second quadrant angle. And your inverse cosine button knows that. So that's where the strategy pays off. When we do the inverse cosine of a negative input, it's going to come out as a second quadrant angle already. So applying that strategy helps us not have to worry about quadrants when we do inverse trig stuff. Comes out 117.3, right? The calculator also. Inverse cosine knows that that has to be a second quadrant angle, and it comes out that way. I've got 117.3 for that angle. And now I can finish it off by going through your law of sines to find one smallest angle, and then your angle sum property to get the last one. So go back to your chart with this. And now I know capital A is 117.3. Put that in. Degrees, that's an answer right there. So if it's an angle answer, it should have your degree symbol on it. That's kind of important. And then B and C. Again, if you're really into the law of cosines, you could use all 3 versions of the law of cosines and go through all of those steps right there 3 times over, and you'd get all 3 answers. But that's a pretty tedious way to go about it. If you get one of them, the law of sines is much quicker to fill in the next one. And 180 minus is really quick to fill in the last one. So that seems like the smarter way to go. So I'm going to get little c from my law of sines now. C over sine c equals A over sine of A, which is 117.3. So I'm going to calculate that, but let me do my cross multiplying kind of solving for things first. 3 over sine C equals 6 over sine 117.3. So 6 times sine of C is 3 times the sine of 117.3. I hope you're getting a little bit of a rhythm with working through these. The steps are very similar on all of them to get angles. I'm going to divide by 6 next to get sine C by itself. I really like to write this down, the result of all of this, and then I'm going to do the inverse sine part to get the angle. But I like to write down what sine C comes out to. So that's, let me see what it comes out to. 3 times the sine of 117.3 divided by, well, the result of that divided by 6. I got 0.4443. And I know this one's got to be second quadrant, so I can do the inverse sine and not have to worry about that. I need inverse sine of that result there. So if you have an answer button, you can just ask for the inverse sine of that answer if that's the last calculation you did. That's nice. So you can figure out how to make those calculations more efficient as you go along. I entered something in wrong, but let me see. Inverse sine of that should be, yeah, it's 26.4 rounded. Capital C is 26.4. That's my smallest side. And then 180 minus that, I can fill it in. So I got 26.4. I'm putting that here. The chart keeps track of these things nicely. And they don't add up to 180. They add up a little less than that. So the difference is going to be B. So I'm doing 180 minus both of those and see what's left. $26.4. Subtraction leaves 36.3. That's my in-between side. That's my in-between angle. All looks good with that. Long problems, lots of opportunities to make mistakes, but calculations kind of repetitive. Each one of these that you do, there's not a ton of variety to it. There's just different numbers. So you want to get enough practice with this where you feel comfortable with the process and you see a few of the different things that can happen, but it's really a lot of the same steps that you go through in solving these things out for the different numbers. You get in a flow with it after a while. So you want to get some repetition with this, get some practice with it through the week. It's our last trig topic. So we're going to wrap up the trigonometry with that and go back to algebra for a while. Y'all need to get in touch with me about which time slot for the test again, because we got to take the test on trigonometry. It's once you finish the homework first, the tests are going to be Monday or Tuesday, depending on which time slot you pick. So let me know. I've got a couple of those marked in already. Others need to drop a note to me to let me know which time slot you want for the trigonometry test, and then we just do. There's system of equations after that, but that gives us an opportunity to review linear and quadratic equations in the context of solving those systems. So it's a nice wrap up that we get to next week before the final exam. So that's what we have ahead of us. We're going to take the test on trigonometry, and then these systems that we do, they're just on the final. So we'll be reviewing as we go along with those. And I'll be watching for questions on this. I expect it's a lot of work, so I expect you might run into some stuff with some of those homework exercises. Let me know if you get stuck on anything. I'll be watching emails, and I'll check in with you all later. In touch.